Okay, so we had this list of ways in which we can calculate the delta H. And that's really what we're trying to get enthalpies of reaction, right? So an enthalpy of reaction is that delta H that I've been talking about. We're using standard heats of formation, which we call delta HF, all right? And I've already introduced to you a formation reaction. And so we're going to use these formation reactions and their delta H's in order to somehow calculate, again, delta H one last time. If you recall, or maybe you've written down that list, I've written it a couple of times, there's been a handful of ways in which we can get the delta H. Going backwards, we used Hess's law the previous class, where we flipped them around, we added up these different chemical reactions such that they determined, the reaction we wanted. We added that all up and we got a delta H. We've used bond energies, right? Knowing that bonds breaking takes energy, bond forming gives energy. We add up the bond energies, we can get an approximation of the delta H. We've used calorimetry, MC delta T, right? And the negative sign, so we can get the delta H that way. And so, and then we had, I think, molar enthalpies, which is really the simple basic definition on how to get it. So this is the final way in which we can get those delta H's. And then the next 3 lessons talk about a new quantity that I'm going to introduce you tomorrow called entropy, and then our enthalpy and our entropy work together to determine spontaneity of reactions, and that's what we're going to finish with. And I've used lots of big words there, but I'll slow it down tomorrow when we get to those lessons. Okay, so first let's talk a little bit about standard enthalpies of formation and what that means, and then we'll obviously use that. Hello. That's okay. Mrs. Murray had to leave. Yes, she had a doctor's appointment. That's the information that she's going to need. Yeah. All right, thanks. Okay. Now, as you're writing that down, I have a handout for you. It's kind of odd. The reason I created a handout, I did try to scan this table, and when I did that, it cut off all the headings. So there is a table that looks like this it's not connected to the day's work, but it's in the folder on the course content, and there are no headings, so there's no units. You have no idea what the columns represent. So really, it's a useless table, and I need to remove it. This table is useful. Oops, 3, can't cut. Okay, so a standard enthalpy of formation, notice that it has the subscript F, and therefore it's molar, it's per mole of a substance. And as I've stated, we've already encountered a formation reaction. I've done an example with it, and I defined it at that time. You probably didn't think it was super important at the time, but now it's becoming super important, so I'll define it again. It's the amount of energy that is absorbed or released when 1 mole of a substance is formed directly from its elements, right? So we're building the molecules, starting with their elements in their standard states as found on the periodic table. And the reason we use the term standard is because very often when we get a table of data, the numbers have been calculated out at SATP, 25 degrees Celsius, 101.3 kilopascals. Sorry, 100 kilopascals for SATP. Not that we're going to be using those numbers. We're not going to be doing anything with the gas laws. But at the university level, if you're not at that temperature and not at that pressure, then additional little calculations need to be done to adjust the values that are in the table from what they're tabulated as. So they're tabulated as a standard value. And if you're working at different conditions, you would need to apply some pretty complex calculations to figure out what the value is at other than standard. So we're not going to worry about the word standard. I'm not even going to worry about that little circle there. That circle tells us that it's at standard, all right? And you'll notice on your table as well, if you've started to take a look at this table, you'll notice there's a column on the left that has the compound or the substance, and then that next column to the right has the delta HF, and you'll notice it has the little circle. And that just says that it's at the standard state measurement, okay? I'm not worried about that little circle, but when you go to more complex chemistry courses and they're going into more detail, then that will become an important little marker. For now, not important, okay? All right, so standard enthalpies of formation, delta HFs, are tabulated enthalpy changes for these reactions that we call formation reactions. So just like if we had a table out of the big book of chemistry for enthalpies of combustion, we know how to do a combustion reaction, some chemical plus oxygen to get carbon dioxide and water. I'm also expecting you to know what a formation reaction is. Element, element, element to produce whatever chemical we're studying or we're looking at the time. That's what a formation reaction is. And again, I've had you write that down in the past, but let's just review what we mean by a formation reaction. So there are some examples of some formation reactions, and I do want you to write these down, all right? So now, on this table that I've given you, you'll notice there are no chemical reactions. There's just a list of the chemicals. And these are two formation reactions. One is forming water in the liquid state, and the other one is forming water in the gaseous state. Now, because they're a formation reaction, the chemical we're interested in is the product, and we're building that product from its elements as we would take them off of the periodic table in their standard states. So when you're imagining a formation reaction, you can almost imagine as if the periodic table itself is a little depository for each of the elements that we may need to put together in some kind of a chemical reaction to produce this product. I did a balanced reaction for you in the past. I'll do one more just to show you, but when I do a formation reaction, I start with the product, I then look at the elements I need, I look at what state they're in on the periodic table. So to make liquid water, I need an H2 gas molecule, I need half an O2 gas molecule, and that will make me an H2O liquid molecule. Notice I need the exact same reactant to produce my H2O gas molecule because I have to form it from its elements in its standard states. Notice the difference between these two reactions, though, is the amount of energy that is, in this case, given off because it is exothermic, negative. The amount of energy that's given off depends on the final states of the liquid or the gaseous water. If I want to make liquid water, it's going to give off 285 kilojoules per mole, and if I want to keep it in the gas state, it's going to give off only 242 kilojoules per mole. Gas state is higher energy than liquid, so when it condenses, it gives off a little bit of extra energy to condense into the liquid. We actually could use Hess's law, if we would like, to flip these things around, cancel out the H2s and the O2s, add them up, which is essentially going to be a subtraction if I flip one, and I could determine the energy needed to convert 1 mole of liquid water to 1 mole of gas or vice versa. But we're not doing Hess's law. Just as one more example, just to show you where the information comes from, what if I wanted to produce CO2 gas? Let's go through this just as an example. Let's say I say to you, write me the formation reaction for carbon dioxide gas and tell me what the delta HF is for it. All right? So, building a carbon dioxide molecule, what am I going to need to build that molecule? Yeah, what do you got there, Megan? I need carbon solid, C solid. Excellent. And I apologize for the dark green. It used to be yellow, but it's switched up on me. Hopefully you can see that. Yep. I need 1 O2 molecule, right? Plus an O2 gas molecule. Excellent. Now you go to your table and you tell me what is the delta HF for a carbon dioxide molecule. This table is split into 3 main columns, so there's 3 sets of substances. We're only looking at the delta H column at this point, so you're scrolling up and down. It's alphabetical by element, I believe, and you're looking for a CO2 gas, and you're looking for what that number is, and I'm going to write down here a delta HF is equal to. And Bethany, what do you got? 393.5? Negative 393.5 kilojoules per mole of CO2. Okay? So that means when a CO2 molecule is formed from its elements, that's how much energy is given off. Are we okay with the idea of formation reactions? Okay. I've got a couple more examples. Don't write these next 2 down. I'm just going to bring them up. Notice in these 2 examples, we're making this particular molecule. This is called propane. And this molecule here, this is called ethanol. They're both fuels. They can both be combusted. Anyway, for the formation reactions, notice that we're stating graphite. Now, that's not a big deal in this course. I'm not going to be tricking you with all the different forms of the elements. But it turns out that there's a large number of forms that carbon can come in. Technically, they're called allotropes. Carbon can come in straight black carbon, like soot. It can come in diamond. It can come in graphite, which is the carbon that is on the end of your pencils. That's the way your pencils write. It's called graphite. It's been determined that the lowest energy form of that particular atom is the graphite version. So we use the graphite as the starting point. Not a big deal. You'll learn more about these allotropes in university. I just wanted to mention it. And again, we can find that information on that table, and if you were to track that information, you'd find that. Now, this last example I do want you to write. It's kind of a silly one, but it is important. I want you to write the last example and then the information that's in that box. Now this last example is stating the obvious, really, but we do need it when we do our calculations. If we want to talk about the formation reaction for an element, and we're going to make that element out of itself in the state that we find it, then I'm hoping it's quite obvious that it takes no energy to create that because it's in the form we want it to be in, and I'm not changing it in any way, and so the heat of formation for an element we define as being 0. It's in the state that we want it to be in. We don't have to melt it. We don't have to vaporize it. We don't have to do anything to it. We don't have to react it. And so the heat of formation for an element is 0. And if you take a look at your table, look at the delta HF column, run your eyes up and down it, and every time you see a 0, you're going to notice that that's for an element itself. You see what I'm talking about? You look up and down there, you'll see a 0 on that page. The delta HF line, every time you see a 0, you'll see that it's an element. All right. The reason we have to define this will become clear in a moment. Okay, so now that we've recalled what a delta HF is, how can we use this to find the delta H? Now, don't write down the equations on the bottom. I'm going to explain to you where those equations come from, and then you can decide which of the two versions you want. So write down the title, leave some space, but what I write above, you could theoretically write it below. I'm going to talk about how we can break these into their elements and then how we can reform them from their elements. So I'm just going to do a little kind of graphic, not graphic, but you know what I mean, just a description of what's happening here. So whether you write the reaction up here and you write what I'm going to write below or above, it doesn't matter. So first thing we need to do, and we're going to look at the reaction for the combustion of methane gas, CH4. We've probably used this example in the past. It's, you know, it's a very simple example. It's got lots of, you know, molecules in it. We can manipulate it. First, let's balance it up. 1, 1, that's a 4. I need a 2 in there. And it looks like I've got 102, 2 O2s. Does that make sense? I got 2 O2s for this. 2 O2s, got it kind of squishy in there. Now, physical states become very important because as we saw, there's an energy difference between whether it becomes a liquid or whether it forms a gas. So let's say that this forms a liquid. We'll make that liquid water. Carbon dioxide doesn't have an option. That's a gas. Oxygen doesn't have an option. At room temperature where we're burning this, it's a gas. And also methane, it is also a gas. All right? And as I've stated, we've seen different ways in which we can determine this delta H. If we knew the bond energies, we could draw the picture, we could count up all the bonds, that's great. We want to use the heats of formation this time though. So what I need you to imagine that's happening here is, I need you to think of a chemical reaction that's going to take this CH4 and break it into its C solid and into 2 H2 gases. So I'm going to be breaking it into its elements. I'm essentially going to do the reverse of a formation reaction. And this essentially is a formation reaction, except I've flipped it around. I'm breaking it apart. It's the opposite of a formation reaction. What do I do to the sign of a delta H if I flip a reaction around? What happens to the sign of the delta H for a reaction if I flip the reaction around and I make the reactants become products and products become reactants? Yep. It changes the sign to the opposite, which means this isn't the delta HF for CH4, but it's negative the delta HF for CH4. It's a negative version of it. Does that make sense to everyone? Since I'm breaking it into its elements, it's not the heat of formation, but it's the negative of the heat of formation. I'm going to do the same with the oxygen, even though I know that this has zero energy, right, because it's its element. But technically, we could write it as the negative of the delta HF for O2. It's actually going to be 2 times the negative of the delta HF. It's going to be 2 times 0, because I'm doing nothing to oxygen twice. All I'm doing here is an accounting, essentially, right? Even though it's 0, we'll be able to put zeros into the equation. And that's going to then leave me with 2 O2 gases. And then for the second part of the reaction, let's imagine then, and I'll try a different color, but my colors are terrible because they're so dark. We'll imagine then that I take one of these C's, right, and I bring it into there, and I take one of these O2s and I bring it into there, and now I'm doing the formation for the products. I'm actually doing a regular formation reaction. I'm building the products. This technically right here is the delta HF for CO2. The actual delta HF, because that's what we define it as. And you can see, hopefully then, that I can do the same thing with my 2 H2s and my O2 that's left, and I can then have, again, the delta HF of H2O, and it's actually 2 of them. All right? And I apologize for the blue. Yeah, the blue is tough. Can't see it at all? It simply says delta HF for H2O. All right. You don't need to write this down every time anyway. I don't ever want to see this on a test. Don't give me that. But if we think about it, here's what's happened. For each of the reactant molecules, I'm going to add up all the delta HFs. This N represents the coefficient, so I would add up the delta HF for CH4 and 2 times the delta HF for O2, and I would put a negative sign in front of it because I'm breaking them apart. Does that make sense? Does it make sense? Excellent. And then when I put them back together, I'm going to add up. Remember, that means sum. Again, the N, I'm going to use the coefficients. I'm going to have 1 delta HF for CO2 and 2 delta HFs for O2, and I'm going to leave it positive because I'm actually doing a regular formation when I make the products. Now, last year when I taught this, when I taught it this way, I thought it was very logical to say negative of the sum of all the delta HFs for the reactant plus the sum of the delta HFs for the products. But in your textbook and in many textbooks, they like to flip it around and they like to say the sum of the delta HFs for the products minus the sum of the delta HFs for the reactants. I'm going to solve the examples using the bottom equation, but I don't care which equation you use. As long as you keep your signs straight, you're in good shape. The reason I think chemists and physicists like the bottom version is because if you've taken physics, you've been trained that delta always means something 2 minus something 1, like E2 minus E1, right, like a delta. And if you think of the products as being the secondary things, then you're kind of thinking as delta HFs 2 minus delta HFs 1, as if it's a delta. That's the only thing I can kind of, reconcile with that. However you want to think about it. Okay, so I like the second equation. I'm putting out there the first equation because it builds from our logic that we used to build it. I don't care which version you use. Let's do some examples. So now you need that table because the table is where you're going to get all the delta HFs. The homework I'm going to give you out of the textbook, they've got their own little table built into the textbook there. It's close to where the questions are. It may not be exactly the same as this table, but you could use this table as well. On a test, I either give you the delta HFs in a little table, or I simply let you use this table, the one that I've given you. Now that equation isn't balanced yet, so we're going to need to balance it. And then we'll use our new equation to find that energy for the reaction. So we've got FS2 solid, O2 gas, F2, O3 solid, and SO2. Looks like we're combusting this material, this iron. If I do the reverse crossover, it looks like it's an iron 4. It's kind of a funny looking thing. I hope I didn't screw it up. I changed this at lunch, like I said. There should be an FS2 on your sheet, and there it is right there, pyrite. So that's like a rock. So it's a type of a mineral. I guess we're burning this pyrite. Let's balance this up. What do I need to balance? Looks like I need a 2 here, right, for my irons. And for my sulfurs, it's looking like I need a 4, right? Let me know if I've screwed it up. And now for oxygens, we can use that fractional coefficient, right, which is fine. And I'm going to have here, what have we got? 3 and 4, 5.5? 5.5? Right, because I got 4 of them in there and I got 1.5 in there. 5.5. 5.5, and I apologize for writing on that O2. Okay, so now we're ready to find the delta H. According to the equation, and I'm going to rewrite the equation. I find sometimes during a test or during something, if I'm writing it, I don't necessarily write the equation. If I know it, I start to write the numbers down, but I'm going to write it for this first one. So it states that it's the sum times the coefficient, and that's delta HF, and that is essentially for the products minus sum, the coefficients, the delta HF for the reactants. So here's what it looks like. I make 2 sets of large brackets, one for the sum of the products, one for the sum of the reactants. I simply go to my products, and I have 1, and now I'm looking for the heat of formation for Fe2O3 solid, and you now have that table, and I need you to track that number down for me. Again, it's alphabetical by element, so this looks like it's in the second column. Fe2O3. What number do you see there? Yep. Yep. Negative 824.2, and I didn't really leave enough room in my little bracket there, but that's okay. All right? I continue on with my products. Plus 4 times. Now I'm tracking down an SO2. Did you find it? I got it, SO2. Negative 296.8, right? Negative 296.8. I'm done the reactants. Close that up, so I've got the sum of all, I've done the products. I've got a sum of all those product molecules. Minus, now I do the same for the reactants. 2 times. Now I'm looking for FES2. I'll take that number as soon as you find it. FES2, yep. 178.2. Negative 178.2 plus, notice, the negative is for the reactants, but I have to sum them all, so I have to add them all up. It's not like I've got a whole bunch of negatives in there. I'm adding them up. So this is 5.5. What's the heat of formation for O2? 0. So still, it doesn't hurt to put it in just to kind of keep our accounting. But that's 0, so that thing kind of disappears. The way I like to do this, and I suggest you do it this way, find the sum of the first bracket, find the sum of the second bracket. Don't do it all in one shot. Because you've got so many negatives and other negatives in there, things get lost. And I know this one from personal stupidity mistake making on many exams. I'm like, what did I do? So then I had to say, slow down, just do one at a time. So just find your total for the products, your total for the reactants, and then I can even give you part marks, right? I'll be honest, when I mark this stuff, I'm looking for this put in properly, then I'm looking for this minus this, and then I'm looking for the total. And if I see that you've got one mistake in here and you've got a different total, I only take one away. But if you go right down to the bottom and you've got it wrong, I'm not giving you part marks. You'd lose 2. Right? So I can see the little steps in there. And trust me, you might think addition, subtraction with negatives should be easy, but boy, oh boy, it's easy to screw it up. What do we have for the first bracket? Somebody got a number? So negative 2011.4. We got supporters on that? Again, I made this up new right now. We didn't do it this morning, so I'm not sure what the numbers are. Okay, excellent. And I will take the reactants version as well once we get it. Yep. You said 356.4? I just didn't hear you. 356.4? And it is negative as well, correct? Negative 356.4? Because there's a negative in front of that guy, right? So now you're going to take that negative number and add that number, right? So again, because you do it this way, you can kind of see where the number should end up. You've got this big negative number, and you're going to add that little number. We should be in the negative 1700 business. Then you can kind of get a little estimation to see if you're on the right track. What do you got?
1,655.
1,655. Negative 1,655 and, yeah, 0.0. And even though I didn't write them in, on our table, these are kilojoules. Okay? Delta H. Questions, concerns on how to run that equation? It's pretty straightforward. We're really extracting some data and applying some logic. Now we can obviously do something with these numbers. So the question then becomes here, part B, determine the delta H if 5 grams of this substance was burnt. Now we've been doing this all along. Every time we've found a way to calculate the delta H, I've always added on a little piece. What if it was 5 grams of this stuff that we did? So this is nothing new. I'm hoping we're not terrified of this stuff. And if we get grams, what do we do? Without even thinking, turn it into moles and then start thinking on where you want to head. So what's the first thing am I going to need to solve this even before I start doing anything? I need a molar mass. I heard it out there. FeS2 32.1 for the S and 55.8. 32.1 times 2, 55.8. 120. 120 grams per mole. 5.0 grams. Again, whatever method you want to use to calculate this stuff, use whatever you want. We're going to go with what I like to use, 120 grams per 1 mole. And in the end, I've got to get kilojoules. So again, I'm to the point where I could use delta H equals N delta HX. But the thing that we got on the last slide technically isn't, oh no, okay. The thing that we got here technically isn't a delta HX. Why isn't this a delta H little x? Yep. It's not per mole of anything, except it actually is. It's per mole of one thing. What is this per mole of? It's per mole of this, but that's not what I'm worried about. This is the amount of energy for 2 moles of this stuff, right? So I could turn that into a delta HX by dividing it by 2. Then it would become per mole of this. Or I could just create a conversion factor from that information. So notice here, and I better bring a question up. So notice here, this is in terms of Fe2S. You've got your work in front of you. I'm not going to go back to the previous slide, but how many moles of FES and how much energy? What am I putting in this little conversion factor here? And don't make me go back because it doesn't work. What do you have there? Bethany, what are you going to put? FES2. Yep. I didn't catch the decimal. What was that decimal? Was it 0.0? Was it 0.0? And we really don't need that many significant digits. It looks like we're going to round to 2 anyway with the 5 grams. So again, you could create a molar enthalpy. You could use that equation, or you could just generate a conversion factor. How much energy are we going to get out when we burn 5 grams of this stuff? Yep. You got negative 34.5, did you say? 5 kilojoules. And I guess we're rounding to 2 significant digits. So negative 35 kilojoules. Do we like that? All right. Again, just to make sure we're on the right track. Okay. So again, once we find a delta H, we can then think of it like the thermochemical equations that we always have, and we can use that to determine whatever. All right. 2 more examples that cover some interesting twists that we can now have on this. So we'll have you write this one down. I'm a fan of a question like this, hint, 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 because it involves a little bit of everything of what we've done in this unit. Did we catch the hints? Okay. Put a little star beside it, however you want to do that. So we're burning some propane, and we want to heat some water from 25 degrees Celsius to 100. We're not boiling it, we're just getting it to 100. In this question, again, I've got 2 parts. Because if I'm heating water, what am I going to need? What equation am I going to use if I'm talking about heating water? Yep. The calorimetry equation. I'm taking the energy of the burning of the propane, and that energy is going into water. I'm heating it up, and I want to heat 500 grams of water. And the question is, how much propane do I need? So this is a system and surroundings question. We've got negative MC delta T. And we've got delta H, which is equal to N delta HX, some molar enthalpy. You'll notice we have all of our information about the water. We don't need any more information for that. If I'm talking about the propane is our system, because that's what's burning. And if I ultimately want to get the mass of the propane, which is the mass of our system, what am I finding first? What am I finding first in all of this chaos? If I want to get the mass of the propane, and the propane is the system, what do I need to get first? What am I ultimately driving for before I get that mass? N, the moles of the system. I need to figure out how many moles of that propane, N, am I going to have or need to get that to that temperature, all right? And then I can apply a molar mass and away I can go. I'll tell you what the formula for propane is. It is C3H8. Now, you need this delta HX. I've taught you how you can use an entire reaction all right? How you can use an entire reaction to get a delta H from what we just did, using our calculations with the heats of formation, and then you can turn it into a molar enthalpy, all right? I'm going to let you guys go. You can talk with a neighbor or work with a partner, but ultimately, we need a balance. We need to use our table with all of our heats of formation. We need to get a number, and then we need to figure out this side, and then we ultimately need to figure out N. I'm going to give you some warnings here ahead of this whole situation. When you calculate this number, it's going to be in kilojoules. When you calculate this number, it's going to be in joules, because our C is equal to 4.18 joules per gram degree Celsius. So you've got to get them into the same unit before you can solve for that N. I'm going to tell you one other piece of information. I want this to be H2O liquid, because you need to pick the liquid or the gas as the combustion product. So this is gas, and this is gas, and they're all on your little form there. So I'm going to pause the recorder just for a moment, so we're not just kind of working away here. Pause. So what did we say this was to balance it? This was 1, 5, I believe, 3, and 4. Is that correct? And when you did that calculation, some of you are finishing off negative 2219.9 kilojoules, correct? And now at some point, we need a molar enthalpy. What is the molar enthalpy for the combustion here of the propane? What can I say in terms of per mole of what? Yep. It's the same number. Why is that? Because there's 1 mole of propane. So I can say that the molar enthalpy in terms of propane is negative 2219.9 kilojoules per mole of propane, because there's 1 mole of propane. All right? And Scott doubled everything, which means he has to divide by 2, which is fine. No big deal. Now, on this side, you're going to get a number, but it's going to be in joules. Not a problem. In order to solve, we either need to turn the delta H into joules, or we need to turn this into kilojoules, as long as they're the same number. What do we have for a number here? I don't care whether you give it to me in joules or kilojoules. What was our MC delta T? 500, 4.18, and it looks like 75. What do we got? No one wants to share. Easiest part of the calculation. Elika's not going to give it up just to spite me. Courtney's looking as if she has a number. What do you got? Negative 156,000. Sorry, the last part. 750. 750, and that's got to be joules, I suspect. Right? So we have a number that's joules. We have a conversion factor that's kilojoules per mole. If we turn that to kilojoules and then use the conversion factor to find moles, we've got it. Or we can rearrange the equation. We could take this, turn it to kilojoules, and divide off our delta HX, and we'll have moles. Either way, it doesn't matter. Again, using equations versus using conversion factors, I don't care. I'm going to use the conversion factors just because it's easier on space. So if I turn this to kilojoules, negative 156.75 kilojoules, which is way too many significant digits, but we'll round back later on. Then I have negative 156.75 kilojoules, and I need to get to moles, and that's kilojoules per mole. There's no reason why I can't do that. Or you can use the equation. Two ways of doing all this stuff. Negative 2219.9 kilojoules per 1 mole of our propane gets rid of the kilojoules. That'll give you moles. How do I turn moles into mass? Molar mass, that was great. You guys are awesome. Boom. I can add that right onto the back end, or if I'm doing separate calculations, I can do the calculations separately. What is the molar mass of C3H8? Has anybody calculated that? Yeah, what do you got, Corey? 50? Is it exactly 50? 50.0, right, because we know it's the three significant digits, grams per 1 mole. So that, in the end, will do it for us. What do we have for the mass of propane needed? So we're just doing our regular conversion factor business here. I was wondering, 50 seemed a little funny to me. 44, I don't think my eraser works, so I'm going to scribble that out into a 44. Got a final number? 3.1 grams. Two significant digits. We could probably keep another one, and it would be, okay. 3.11. 3.11 grams of propane of C3H8. All right? Like I said, I like that type of question. It kind of covers a little bit of everything of what we can do in this, in this particular course. So, like I said, big hint on that. Okay? Kind of a neat question. All right, I've got one more that I want to do. Yeah, I know it's a long lesson today, but I got one more. It would be quite a bit. Yeah, it would be quite a bit. But it's an important question in that it really forces you to think of all of the stuff I've taught you about, right? It's one of those questions that gives me a good measurement on whether you truly know your system versus surroundings, whether you are comfortable finding a delta H using delta HFs. It's got the whole deal. But yeah, it's worth quite a bit. So, this last example is an example of how we actually find heats of formation. Many heats of formation are not easily obtainable. Benzene is a complex structure, and it has a formula of C6H6. And I can't just form benzene by taking some carbon and some hydrogen and heating it up. It actually turns into other molecules. So I can't actually do that formation reaction. But it's important that we have a complete table of formation reactions so that we can do the stuff that we've been doing. So this is a method in which sometimes we can find formation reactions for chemicals that are not easily formed in a formation reaction. We're starting with a molar enthalpy of combustion. This is not formation. This is the combustion reaction for benzene. Gotta put my pen down again. C6H6, and we're combusting it, and again we're getting CO2, and again this time it's telling us again to have H2O liquid. Again, O2 gas, CO2 gas. All right? Now the difference in this question is this number here, this is the delta H. In other words, they've told us the answer. They've told us the answer to the question, and we're looking for one of the delta HFs that are in the question, one of the numbers that are in the middle of the equation. So in a question like this, I give you the reaction, but I give you the answer. It's the answer to what we've been doing. It's the delta H. And now we're going to then look for what the number is on the inside. So that's the way we're going to set it up, all right? So I'm going to just rewrite the equation again, delta H, and I'll explain why in a moment. Sum N delta HF of the products minus the sum N delta HF of the reactants. I'm going to my table just like I normally would, but the only difference now is this is the heat of combustion. For 1 mole of this guy, this is the answer. So it goes here. It goes to the left of that equal sign. First I have to balance though. I forgot to do that. 6, 6, 3, because it's half the number of H's. And then I've got 6 O2s and 1.5, 7.5 O2s here. 7.5. I do the question just like before. The only difference is I now know negative 273 is the answer. I now fill in everything as I normally would, and when I get to the delta HF for the benzene, I'll put an X in, and I'll just solve for the X. 6 CO2s. We've been using CO2 a lot. I hope you can find that number fairly quickly. Have we got our CO2 number? You could even steal it from previous questions, probably. It's fairly big, 380 something, I think. 393? 393.5. Negative 393.5 plus 302 liquids. Again, we've been using that one a lot. 285 point, I don't know, something. Sorry? 285.8. Negative 285.8. Close the brackets. Minus. There's only one. There's only one C6H6. That's what I'm looking for. So in this type of a question, we're looking for one of the delta HFs. And then this is going to be plus 7.5, and that's a 0. But that's okay, we'll still add it in. Negative 3273 equals. You could go ahead and calculate that down into one number. And notice all we're going to have on the back side is minus X. Once you get that number, manipulate the equation, solve for X. I'm also a fan of these, by the way. Fan of this type of question. Just saying. The common mistake made by people in this question is to think that this number is the heat of formation, putting it in where the X is, and then solving for something which isn't really what we're looking for. What do we have that's in the bracket here? It's negative and it's fairly big. Yep. 3,218.4. 3,218.4. Supporters on that. Now we've got to do some algebra. I've got a negative x on this side. The way I would handle it is I would add the x to that side and get x, and then I would add this number to this side, right? Does that make sense mathematically? Hopefully we're able to do this math. So negative 3218.4, there's my number there. This is coming to the other side, positive 3273. And it's looking like it's a little endothermic. I think the bigger number is the positive number. Yeah, it's a little endothermic. Sorry? What is the number? Oh, Elika almost gave up an answer, but she tried to pull it back. 54.6. So positive 54.6 kilojoules per mole of I don't know where that's coming from, C6H6. And this is a delta HF, and therefore per mole is the correct unit, because we found the delta HF. And that's the way many delta HFs are found. Are we got a mistake in here? It's not that exactly. That's okay. What that means is, they obviously found another way to calculate that value. Again, a lot of these delta H's are kind of estimations. We're not too far off. We're okay. All right? Some homework problems, and that's that.